Welcome to Maple Structure, and in today's video I'm going to show you how to analyze single overhanging beam with uniformly distributed load. Let's get started. First, let's take a look at the structural model. It consists of two segments, the main span between roller and pine supports and the overhang, which acts as a simple cantilever I explained in my previous videos. The beam is loaded with a uniformly distributed load along its entire length with a value of 4 kN per meter. The length of a cantilever segment is 2 meters and the main support segment is 5 meters. As we did with simply supported beam, here we need to figure out support reactions as well. Now, let's introduce the x and y axis. Consider support reactions are directed upwards at both points A and B. If it's wrong, the equations will show us minus, so don't worry, it's just an assumption. But here is actually obvious, because there is only distributed load directed downwards, and our support resists to it causing support reaction in opposite direction. To make analysis simpler, let's remove distributed load with concentrated force by multiplying its intensity and the whole length of a beam, which we can define as the sum of two segments' length. Now, let's sum all the vertical forces along the y-axis. These equations include two unknown reactions, so we need to introduce another equation. I suggest sum all the moments about point A, which will give us equation including only one unknown sum reaction at point B. And please, pay attention to how the moment arm of the concentrated load was found. It's not difficult, but it may cause some mistakes. From this equation, we're able to figure out reaction at point B and then easily put it in the first equation and define reaction at point A. Alright, now let's move to the next part of analysis. If our beam is loaded with vertical forces, it causes two internal forces, shear force and bending moment, so we have to determine their equations along the entire beam length. And I suggest start with plotting shear forces diagram. As I mentioned before, our beam consists of two segments, and let's name them as a segment 1 and the segment 2. And let's take a precise look at the first one by using method of sections. For that, let's cut our beam somewhere in the center and focus on the left part. Well, the system is in equilibrium, so it simply means that every single part of a beam should be in equilibrium as well. So if we cut our beam, we must replace the removed part with internal forces acting at the cut. Let's show all the forces we have in this cut segment. Support reaction at A point, our replaced distributed load, and internal forces itself. Now, by summing all the vertical forces in a y direction, we could determine the shear force equation. This equation is linear, and it means we should take only two values of x and then plot the diagram by connecting those 2 points. I suggest took two boundary points, where x equals 0 and where x equals the whole length of a segment. And now you can see the diagram for this segment on the screen. Alright, now let's take a look at the segment number 2. By using sign convention, we direct the internal forces as you can see on the screen. I explained the sign convention in my previous video, by the way, so if you don't get it well, please watch it before I continue with this one. Here we also have to sum all the vertical forces and determine the shear force equation. Here we take 2 points as we did before and easily plot the rest part of the diagram as you can see on the screen. Here we could easily define that our diagram is made right, and here's exactly how to get it quickly. So let's take a look at the point B, where we have some kind of jump between two values of shear force. The trick is to sum the absolute values of shear force, and if we did it right, the sum should be equal to the reaction at this point. As you remember, reaction at point B equals 90.6 kilonewtons, and the sum of the shear force values on the diagram equals 8 plus 11.6. which equals exactly 90.6 kilonewtons. And the same thing is at the point A, where shear force equals exactly to the reaction at this point, 8.4 kilonewtons. So always check those jumps while you're plotting the diagram. It's actually the easiest way to make sure you're doing it well. Alright, let's go to the plotting bending moment diagram. For that, we need to analyze those segments again and write a sum of moments about any point. Obviously, we take into consideration the point of the end of the section, and let's name this point as a point C and sum all the moments about this point, and then we easily get the equation you are seeing on the screen. As we did before, we're taking two boundary points where x equals 0 and x equals 5 meters. But here's the catch. We cannot just connect these 2 points somehow. The diagram has parabolic shape as our equation is quadratic, so there's a maximum point we must determine. To do this, we must take a look at the relationship between shear force and bending moments. As you can see here, that's differential relationship, and the meaning of it's pretty simple. We always consider a point where shear force equals 0 is the point where bending moment has its maximum value. All we have to do is to define exactly where shear force equals 0. To do this, we must take our previous equation of shear force and consider shear force equals 0 and then determine the value of x. So here you see x equals 2.1 meters. So now we just have to take this value of x and put it in the bending moment equation for the first segment, and then define the maximum value of moment, and now we're able to plot the diagram for this segment. Isn't it easy? So I hope it wasn't too hard to understand, but if you have some questions left, I'll be glad to answer them in the comments below. So the things are simpler with segment number 2. Here we also consider the cut point is the point C and sum all the moments about this point. After writing the equation, we have to put here two values of x, 0 and 2 meters, and then we can easily plot the rest of the diagram. But do not forget about the shape of the bending moment diagram. As you remember, the bending moment equation is also quadratic, so it simply means we have to connect these 2 points with curved line. And on that positive note, I'll wrap things up. If you have any questions left, I'll be happy to answer them in the comments below. That was Maple Structure. Peace.